Yes. So the main principle behind it is that you have this interface where you can do a bunch of tasks that I'm going to present to you today. You have a upper layer which we call SerialFIB driver, which basically then talks to the AutoScript that you probably already know, um, in order to do certain actions with the microscope that you would need in order to perform tasks like automated lamella prep, 3D clem, which is basically just an extension of the lamella prep where you put your patterns, then volume imaging and um, more specialized tasks like preparation of lift out trenches, etc. And then there's a scripting interface where you can use all these commands that we've already implemented in order to do your own stuff. Good. So with that, let's jump right in. Have a look at how to set up a position. And let me close this so that we go from scratch. So first of all, you just do your usual thing. You load your sample, right? You GIS code that. You might even spot the code if you want it. You identify positions, and for now, I have some saved in here. Okay, this is Klami cells, as you might have recognized, nicely provided by Manon. Yes. So, and I've set the coincident point already quite okay-ish. So you have the same position basically in both beams. And then you go to the support PC, and there's going to be this tiny icon here, SerialFIB. Just double click that, and it opens up the GUI. And the first thing you do is just that you decide where you want your data to go. So set output directory, and then we can go into some folder. I've just set up a folder structure already beforehand. So everything that you save is going to go, like in the automated run, is going to go there. Then next thing is that we have these tools that I described beforehand already, this LamellaDesigner, Volume Designer, Pattern Designer, ScriptEditor. And for a simple Lamella milling task, you just use the LamellaDesigner, which then gives you a user interface like this. You can type in your current, whatever you'd like, your time of that step. You can add some steps. You could even, I don't know, say rough mill 1 by double clicking and changing the name, rough mill 2, and so on and so on. And then you can decide how thick your lamella should be and how thick your patterns should be. And I'll explain afterwards how that is then translated into your patterns that are actually going to be used for milling. Same thing you could do with the next step, and so on and so on. And then you can save this out as a file just by, I don't know, going into the protocols and typing rough mill protocol. Good. And I'll go a little deeper into that later. But basically, you then end up with this protocol file, which you can set in these settings tabs for all these tasks. So for example, for rough mill protocol, you can just go in there and say, I want my Klami rough mill protocol. Same goes for fine milling protocol, it's fine mill protocol. And then we need to set up our position itself, right? And for that, you can take an ion beam image by simply pressing this button here, take ion beam image. And then what's going to happen is, since I can show you that, we've been waiting quite some time for aperture to be replaced. And actually, if I go to the 10 picoamps, which would be the standard here, and you check here in the bottom how much 10 picoamps actually translate with our old apertures at the moment, it's 100 picoamps. And that's obviously not good because you're going to expose your sample a lot. So what you can do then is just in this tab, it's still in testing because I haven't encountered it, but right now it seems to be very hard to get aperture somehow. So you can just change your alignment current if that's happening for you. And for now, I'll just go with the 1.5 picoamps. And you just press OK, and it's going to take that for alignment. Good. So now you can, if you had multiple images in here, and we already see that by going to 10 picoamps, we changed the brightness contrast a lot. Let me change that back and take another image. You can, by double clicking in this image buffer, you can zap through these images that you took. And now we want to set up a lamella position, right? So for that, what we do is we need to draw patterns in this alignment image view. We create it by double clicking into this anywhere, and it will create one of these patterns here, as you see. You can then press F5 to go into full screen mode, since it might be a little tedious in the small window. And we see already that with the 10 picoamps, it's maybe a little too noisy to do. But then you can just decide by left dragging, you can move this pattern around, and a right drag is going to resize it. And what you want to end up with, and again, I'm going to explain a little more on this later, is something that looks like this, more or less. And again, there's going to be a figure in the slides, but basically what this decides is that the width is given by the central pattern. And if you wanted to know how large that actually is, you just go by pressing F5 back out of the full screen mode, and you're going to have the width of these patterns from top to bottom. So what you're looking at is pattern 1 always would be right now 8.7 microns roughly, right? So that's going to be your width, the width of this central pattern. And then the reason why we decide to have these top and bottom pattern is that it decides for you, or this is where you decide where you start your rough mill ablation, right? Because you want to not mill on a grid part in order to not compensate your platinum layer. And therefore, the uppermost region and the lowermost region of these two patterns is going to define where the software starts rough milling. Good. We can toggle out of this view again. We can add this position to the lamella positions. And then when we simply select, we can also give it a label. I don't know if you do correlative stuff or something like that. You could call it like the feeder view. We select the position that corresponds to the image that we want to use. We simply press Save Image and Save Patterns. And then you saw maybe that two numbers here appeared in the back panel, which directly correspond to the numbering in the image buffer. So basically, if you zap through this, the patterns are saved for that position in this image buffer, and they're directly going to correspond to the stage position that you saved here. Good. And after that, you could, for example, save your settings in the folder you're working at, so that you know which settings you were actually using. And as well, save the session so that you can go back to the exact same thing that you had in the graphical user interface beforehand. And then by pressing Run Rough Mill Protocol, for example, you're going to trigger the rough milling protocol that you defined. And a little thing is going to pop up where you can cancel this operation. So let me just press this. So you could, in theory, cancel this. And then let me show you what's happening on the flip side. So basically, it realigned to this item where we were using the 1.5 picoamps. And now it goes through the steps that I defined. So 0.3 nanoamps until a thickness of 5 microns. Then another step at 0.3 until a thickness of 3 microns. And then until a thickness of 1 micron. Yeah, so it starts milling now. And while that's going on, because it's going to take some time, let me just jump back and tell you a little how these files are defined from the Lamella view, LamellaDesigner. Okay, so you saw these three patterns that we drew in the graphical user interface, and they're basically deciding where your lamella should go by the middle pattern, and as well the Y max, so the extreme points for rough mill ablation, right? So the upper and lower one is going to define that. And the width is then again given by the central pattern and the width of that. Good. And from there, it's going to simply be a text file, basically, that's going to be translated into lower parts, but this is just less tedious for you as a user to use. You can directly create them from the graphical interface, as I showed you beforehand, or you just go in there and change parameters slightly by yourself if you wanted to. Yes, and that's simply going to go through this protocol for each step, create the patterns, and just mill for the milling time that you assigned. And the reason why we have the difference between, if I go back to the graphical user interface, the difference between run rough protocol and run fine protocol is that the fine protocol is not going to take these extreme points into account, so that you don't have gigantic patterns where you don't need them. Yes, so that's kind of the logic behind the parameters that you set in there. And this I already showed you, the LamellaDesigner itself, and how to create such a protocol. And these things are okay. So these protocol files are just for your convenience. It's because Lamella milling is obviously the most important or most used task for these kind of operations. It's just going to be tedious to define that from a central point and think about all these parameters that you would need. The only thing you want to know is how thick should my lamella be, basically, right? But at the end of the day, this is translated into the lower unit, which we call pattern files or pattern sequence files, which is simply going to define it from a central point again, and then with associated offsets in X and Y. So in theory, you could create, using that, other kind of routines, such as, I don't know, I use it a lot for lift-out trench milling and to decide where my lift-out trenches actually go. And this gives you the ability to basically do whatever you want, as long as you can define it in these kind of coordinate systems. Good, and there's also a pattern designer that is associated with this that I can show you later. We can double check on our microscope actually, because it's changing the currents now. Yeah, so it just goes to the next step and then starts milling again. Great. Yeah, so this is just a graphical representation of these lower level files. Yes. So the next thing would, I guess, be talking a little about the use cases, but now I'm confused. This I already talked a little about, or just an example of what this can then look like. A very nice cell milled by Sarah in this case. Yes, so for using correlative imaging in this kind of framework, you can basically just, I mean, it's very simple actually. We simply created a interface to 3DCT to load the output files from 3DCT. Because what I mean, I've seen a lot of adventurous methods of how to, for example, translate your correlation spots then to the ion beam image, where people would even go with, I don't know, transparent foils or something and draw the cell on the screen and then put it back and stuff like that. And here you simply can load the image that you took for correlation, as well as the output from 3DCT, and decide based on these correlation spots where your lamella should go. And I can show you that in the user interface later a little more detailed. Yes, so at some point This should change. Should change the currents again. We go to the next step. So maybe we can at least see the transition ones. Yes, exactly. So now it will go to 0.1 nanoamp, as you see in the top left. We will take another image for realignment of the current and simply put the new patterns there and start milling again. Yep. Great. So another use case that we're going to exemplify later as well on the microscope is obviously volume imaging. So removing a slice with the ion beam and imaging it with the SEM again afterwards. And we, in the definition of the site, we tried to stick actually to this general theme of having 3 patterns, so that you could use the same patterns basically for milling your lamella after you've volume imaged them. So it starts here in the top and then ends wherever your the top of your lamella pattern is, and then you can just go with the next protocol in order to produce the lamella in there. And if you push parameters a little and obviously go with a little more dose than you would usually expect, you can get decent results. I think here exemplified on chlamydomonas cells, where you can see the nucleus quite nicely with NPCs in there. And if I just local contrast, so Klahi filter that for you, you can really see stuff like the Golgi or the nucleolus here, as well as thylakoid membranes quite nicely resolved, and NPCs within the nuclear envelope. And this was all collected then with the same software that I'm going to show you later how to set up. Yeah, so right now we're still waiting for the rough milling to finish up. If there's questions, just stop me, right? I mean, yes.
Very nice. When I just have a question, how do you set it up now for multiple sites, milling sites, and how is it then done if you mill always step by step, each rough milling, and then you return to this area to continue?
Yeah, so basically in this table, you could have a bunch of positions, right, with corresponding images. And then, for example, the run rough mill protocol would go to whatever you set. So in this case, 1 micron, and do that for each position. And you could go back. And so what people tend to do is then after rough milling to look at the sites again, adjust the patterns a tiny bit, since things might not move very linearly. So they might just deform in different ways at different positions. It has worked without doing that, but the success rate is just higher if you go back. And this is what we're going to do now, actually, to go back and redefine a little, adjust a little these patterns for fine milling.
For the polishing, for the exactly. Final step. Okay. And can you always then also, let's say, you set up the steps in the beginning, and you make a mistake? Is it possible to delete one or go back and edit one of these positions which you set up?
So I mean, the images are all saved with the patterns, right? If you change something in here, like the positions, it's going to directly be translated as well, and you can go back to the positions as well by going to XYZ by simply selecting that. And also, if, for example, you identified your positions in the ion beam or something, and afterwards you're going to set the coincident point properly, you can just press update Z. And basically, every pattern that you have in here, every position that you have in here corresponds to a single lamella. And you can just go back and adjust things as you like.
Very nice.
So let me quickly show you where we're at. This is what our site would look like at the moment. So I already see that there's something maybe not so nice happening, but we're still gonna set this up again. So either I just delete this position or something, but I can simply take another ion beam image, right, which is corresponding to what we just saw. And then you can just toggle back to the second one, select these by simply clicking on them, pressing Control to select all of them at the same time, and then Control C, Control V them. You can go back into full screen, just adjust this thing a little because you already saw that it moves a tiny bit because of this nonlinear deformation. And actually, Herman looked into that a lot and had some nice plots on some nice ways of how to visualize that at the end of the day that you could show maybe later as well. Yes, so we go with something like this, I don't know, and then you would do that for each position to make the success rate a little higher. You simply, again, press these buttons, Save Image for Alignment, Save Patterns, and then it will reassign these new images to that position, and you can go with the fine milling. If you wanted to go to one go, you can just put additional steps into the rough milling that go to the same same thickness, right? I mean, you're not limited in a sense in how far you take these steps. So you could say that, I don't know, the last one would be 0.4, so 400 microns in thickness or something. And side note actually there is that since we're working with soft material, usually if you have a separation of something like 400 nanometers in this case, it's going to be, so this is usually what we use as our final step, because you'll end up with a 250 nanometer lamella more or less with these separations, because your beam just mills more than you would expect based on the pattern positioning. Yes, so we can go back to this and press the run final protocol. Yes, so let's trigger this run fine protocol. We're going to have a look again. Those are the patterns that I defined in the protocol file. It's going to go back to 1.5, as you see in the top left. It's going to realign to the position. At some point, it takes a little because the apertures are homed. So basically, the AutoScript waits until everything is in the right position with the apertures, while you as a user could already take images before everything is the right position. And you can see that sometimes at your ion beam image, if you change currents and take a snapshot directly afterwards, it's a little off somehow. Yeah, so this will then start the fine milling. And you could obviously do this for several positions, and I can also set that up afterwards if people are interested. Just when doing this live, it's a little easier to demonstrate that way. Cool. Yep. Yeah, so just a quick note on this pattern editor, so the pattern sequence files, which everything is translated into, and it's like the lowest level that you can use. You can also use them to do different other geometries that people might not have, or that we didn't think of when we created these use cases. And one example would be the lift out, where take the output from 3D-CT 2D correlation. I mean, from this correlation again, you can load the same 2D, in this case, image into the software again, and then get little, let me go into full screen, get little green dots where your correlation spots would be, and can decide on your position based on that. And that's kind of then how I do this, for example, here with an egg chamber, where the fluorescence data looks something like this. And then you can just take this chunk, take it to a Titan, and image that. Great. Last but not least, there's the new use cases that I'll talk about for the theoretical part, where simply, I mean, everything we have in there is in the script editor, and the documentation is in process, but essentially you can call all the functions that we use during implementing our automation stuff, something like, I don't know, the stage position or something you can change simply by calling fibsem dot move stage absolute or move stage relative. You have access to the images that you took beforehand in the graphical user interface as a list, access to the patterns, and then you can do whatever you like based on the functions. And also this is simple Python, so if you wanted to include some other packages, you can also do that simply in there. So what it does internally is simply to write a file together with a pickle with the images, etc., that is then just run. So this Python script that is written out with the images, etc., is written out, is then simply taken for the option. Sorry, I got distracted because the fine milling is done. And let's see if something decent. So this actually cut into it a little, I think. So my positioning might not be ideal, or maybe playing with the pattern distribution and milling time might resolve that. But in principle, it looks okay-ish. If you, yeah, could have been nicer, but that's what we got right now for this position. Okay, great. So let me move to the slice and view position to show you that real quick. So I just set up a position where I already milled a little window into the cell. Ah, goddamn it. Yep, something like that, I guess. Okay, then let's take the ion beam image at that spot. Maybe. Yeah, I think this is already quite okay. Something like this, maybe that isn't out. Great. Zoom in here a little more. On the SEM side. Perfect. Then we go back to our user interface. We simply delete this position. We don't want to do anything there anymore, right? We add a new position, and then we have to decide on our volume imaging parameters. And for that, there's this volume designer, where you can then set a milling current, something like, I don't know, 0.5. You set a milling time, 15 seconds, or maybe let's go for 1 nanoamp. A slice thickness, in this case, I'll do 100 nanometer slices. And then there's these functions: focus, realign, SEM, as well as FIB. And arguably at the moment, auto-focusing on these surfaces is actually super hard. And so far, I haven't seen a single program that actually performs anywhere near reliable on it. Also, the commercial softwares aren't really doing too well, and I'm trying to figure that out. So at the moment, since your depth of focus of the SEM is actually quite good, you should be fine not focusing for 5 to 7 microns actually. So the images that I showed you beforehand on the klumpe was all focused once on the position and then just milled through and imaged through, because that's still tedious. Yeah, I mean, we could try to set this just that you've seen at once with the initial focusing, since we cannot really put a lot of dose on these guys right now anyways, because the imaging is just going to take too long. Let's say something like, I don't know, 0.25 microseconds in a line integration of 4, and you set your whatever you want. I mean, at the end of the day, I want to have that you can set the pixel size in there. But for now, it's just you decide about your horizontal field of view, right? You save that file into your protocols, call it SerialFIB params or something like that. You close this again. You can say settings, set SerialFIB params, go to protocols and just select that file. And then we're going to delete the stage position. We take an image at the position where we are currently, and we just create again the patterns that I showed you beforehand. And then this would end wherever the uppermost region of your lamella pattern would be, and also the milling width is again defined by your lamella pattern, right? And then just for completion, we put the other pattern in there as well. We add this position, we select whatever position we want it. You can give it a label if you want, and just press save image for alignment and save patterns again. And then you just simply press run volume imaging. Okay. And then it's going to create all the patterns that it's going to need. Then we're going to see that the autofocus fails, I think, but maybe we're lucky today, because there's just not much contrast that you can put on in a short time to focus, and the charging actually kills you because your contrast even changes over time when you take the focus imaging, the focus images. So if someone has an idea, I'll be happy to hear and implement, because at the moment I couldn't find anyone to have suggestions, and I've been working on that for quite some time. Yeah, so let's see how the autofocusing does. Yeah, I think we are pretty much, maybe. Okay, that doesn't look too bad actually. So once the autofocusing is done, the first pattern is going to be passed into the ion beam view. There's sometimes remnants because the AutoScript clear pattern function sometimes have weird hiccups, but this pattern here on the bottom, don't panic. It's not going to destroy your sample. It's not actively milling, it's simply there in the visualization. And then we already see an image coming through of, thylakoids that you see in this, a little bit of other features. This might actually be, I don't know, Klami experts, is this Rubisco? I don't know. Yeah, the pyrenoid, I guess, I don't know. And then it just goes through the entire volume that way and saves the images into wherever you set up your system. So basically in this folder, you're going to have 0, which is your setup. So this would change with your label, but since I didn't give it a label, it's called 0. And then 0 out is going to give you all the patterns that are used for milling, as well as the images that are used for realignment, etc. And then output would give you your slicer view images, for example. And now let's just wait until there's at least a couple. And we're also providing the analysis scripts that we use to get rid of the curtaining, for example, and stuff like that. Yeah, great. What have I not shown? The custom pattern files, I guess. And then we're done, I believe. Yeah, so this would just X through. Sorry, yeah. It sounds like there's a question. No?
Yeah, just a comment to this focusing. That's I was thinking, would it be possible to, if you would have next to it where you are imaging some lines milled into the sample, like little trenches into the sample that goes quite deep, would it help to image because you would have some pattern and you would then mill it as well and always focus on that pattern? But you would not use it for the imaging, but only for the focusing.
But because focusing of the SEM, you mean?
Mm-hmm.
But wouldn't it change with the? So you need to focus somewhere on the block face itself, right?
Yeah, you would have it. You would have it in the same. You would be also milling it, but this would be just like a auxiliary area for focusing, where you would have a milled lines which would go deep, and you would also mill them. But because they would be like a pattern, maybe the charging would not be so strong.
Mm-hmm.
I mean, I don't know. It's just.
It's actually a good suggestion, I think. So you kind of like a sacrifice position that.
Mm-hmm. Mm-hmm.
Okay, so maybe we just check out a few of the images that just came in, and you can see already with these parameters it looks okay, I guess. You could push it with higher doses, obviously, but in principle, it gives you an idea already of how your surrounding looks.
And Sven, can you maybe tell us what is then the dose if you are approaching to the, since you don't know when you want to stop, I guess, but what is the maximum dose you can still do and not to damage then the lamella for transmission microscopy?
Yeah, so dose we're not quite decided yet. Mm-hmm. But dwell time I can definitely tell you. So dwell time at 13 picoamps is something like 0.25 microseconds and then a line integration of 64. Mm-hmm. So 64 times 0.25 at a pixel size of 3.8 nanometers was usually, when you take two images at that, it starts bubbling. So I assume that's the region where things get messy. And it's somewhere in the 1-digit electrons per angstrom squared, I would say, in terms of dose. But you have to take into consideration that we're not at 300 kV, but like 3 kV, right? So you have a cross section. Your cross section gets a lot bigger, and therefore you can put less dose on the sample before it starts blobbing because the damage is just higher.
But right now you're also milling with current 1 nanoampere. Is that okay for then afterwards to? I guess then anyway you mill deeper to produce the lamella again. Mm.
Yeah. So I mean, maybe the other people can also comment, but at least in my experience, 0.5 nanoamp to 1 nanoamp. If you remove something like 200-300 nanometers of the top afterwards, I mean, even less, I guess, would still be okay.
Thank you.
Any additions, Sarah, or you agree with me on that point? Okay, great. So last but not least, let's close this and cancel our operation here. Then we will see that it's just collecting the last SEM image. Yep. Great. And then we can simply go to a different position. Now I'm getting confused because I have 3 mice around here. Okay. Great. That stopped. Let's go to another position. Go to. Let's go to alignment current again. And the last thing that I wanted to show you was the pattern editor. So how to do things of your own that you want to do, whatever it might be. So first there's the pattern designer, which is, I mean, it looks very similar to the LamellaDesigner, but the LamellaDesigner is simply focusing on this lamella thickness and the sizes of the patterns, right? Well, here you can do as many as you want. I don't know, you can put whatever values you want to put in there. And I think the offset is just a little too high, basically. Let's just make a few. Yeah, and you can put as many as you want for as many steps as you want. Obviously, put a certain current to that, and then it's going to take these files in order to decide which kind of patterns it wants to mill. You can decide on the pattern type as well. So usually for larger stuff, I take cross sections. For more fine things, I take the regular patterns, and that's about it. And I'm simply going to show you one type that I already prepared beforehand. So set custom milling, and then zoom gets into my way. Okay. So let's just go to this one. Then we just take the random pattern file. I can show you real quick what the pattern file looks like. Simply again a text file where we're gonna create a little rectangle, actually a block for example lift outs. So again, with the same procedure, right? We just save this position, we delete this position because we don't need it anymore. We take another image in the ion beam. We don't see much, maybe for visual reasons, we just take one where we see a little more. This is just because of the 1.5 picoamps, right, that we're using currently due to our bad apertures. Let me just put the contrast brightness again. Yeah. And then you can just draw the same logic, right? You select the position that you want this to correspond to, and you press again these two buttons, save image for alignment and save patterns. And then there's this button, run custom pattern file, which is simply corresponding to the custom milling here. And if I press that and go back to the microscope, you'll see this. Yeah, I mean, there you actually see that my dimensions are a little weird versus cells, which I find sometimes a little funny. And then it's just going to start milling that as well. Yeah, and the script editor. So it's going to start milling at 1 nanoamp now. Just same procedure as you've seen a lot now. I'm going to take the image at 1 nanoamp, realign at that current. So yeah, there's the new image, realigns, and then it starts milling at some point. Yeah. There we go. Let me just cancel this for time reasons and show you real quick the script editor, which you can just open here. And there's open script and open library. So this is kind of associated again with the numbering in the library. So you could also distribute these scripts or something. And then the library is simply a certain amount of scripts that you've written. And OpenScript is simply going to put a script to wherever you are at the moment, rather than opening an entire library. Same goes for save functions of that. And with that, I think we are there.
Maybe a question about the correlation. So so how does that work? That module, can you like do targeted milling with beats, or you can click them, or how does it work?
Yeah, sorry, I completely forgot about that actually. Let me go back because I wanted to show this. So you do your normal 3D-CT. I don't know what you guys are using for correlation, right? But if you did your correlation with 3D-CT, I just have some test images here somewhere. Unit test images, yes. Then you get an output that is called 3D-CT correlation txt, as well as your initial image that you please save as 8-bit or 16-bit and not as 24-bit, because that's still giving me problems. Okay, so this is the image that you would have been using for correlation. This would be the output from 3DCT, right? Which is just the markers that you put in there. And then in the software, you can simply press load correlation images, or same under, I mean, these trigger the same actually, load correlation images. Then you maneuver to your images that you took for correlation, developing unit test. First the image that you took, and then the output. And the only thing that changes then is, oh, sorry, let me go to this image again. The only thing that changes then is that it gives you these little green dots to guide wherever you put your lamella patterns, right? And I know it's a very simple approach, but this would then be kind of how we set up our correlative imaging. So you can simply decide based on these where to position your lamella. And this thing is going to take, so the software is going to take the original image for realigning, right? So as long as your realigning works properly, and we haven't had much problems with that, that should directly correspond. What you can also do, what I can simply show real quick, is if you, for some reason, don't want to do that, but still want to know precisely in your FIB image where your correlation spot would be, is that you can go and just select your image from the image buffer, and there's something called align to image buffer. So it will take this image and align to that. And let me just trigger that real quick. But I need to be on the microscope PC to show you what's going on. So it's going to go to 1.5. It's going to take that image buffer image in order to realign to that position at some point. Yeah. Okay. So now you should be in the same framework as you were when you took that image for correlation, right? And then you can say draw correlation patterns. And if you had some correlation spots loaded, that's going to draw patterns. I'm just going to full screen where the, I mean, this doesn't correspond to the position because we didn't do the correlation on that position, right? But the correlation spots would then be, I see them as little arrows, these patterns. So the correlation spot would be at the right turn spot of that pattern. So you could just take those, put them to not active, and now precisely in the framework of your original image where your correlation spots should be before milling. But at the end of the day, you can just use these spots in order to guide the automated setup in the main interface, right? I want to thank the people involved, Sarah and Herman, for the great fun we had developing this thing. Manon for the sample, my two bosses here in Pritzko and Martin Beck for letting me do what I do, I guess, and Yuya Mohammed for really pushing this project. And you guys for your attention.